Hey everyone, welcome to another deep dive, and today we're going to be talking about AI. Specifically, we're going to be looking at this really cool research paper. It's called Simple Test Time Scaling. And it's basically about, how people are always trying to make these big language models bigger and bigger.
Right.
Well, this paper is about finding ways to make them better, not by making them bigger, but by kind of changing how they're used during testing.
That's right. You see, the traditional approach has always been just to throw more data at the problem. More compute power, just make them bigger.
Yeah.
But this paper is exploring a different approach. It's about making the models smarter, not necessarily during training, but during the testing phase itself.
Oh, so it's like giving them like a study session right before the big exam, right?
Exactly.
Instead of cramming more information in, you're teaching them how to use what they already know.
Yeah. And the really fascinating part is they actually achieve some pretty remarkable results
Yeah.
using a surprisingly small data set. They call it S1K, and it only contained the 1,000 questions.
1,000. That's it. Wow. I am intrigued. What makes this S1K data set so special? Why 1,000 questions?
Well, each of these questions was meticulously selected to really challenge these language models. They focused on quantitative reasoning, so think like complex math problems, scientific questions.
So, like, they made these AI models really sweat a little bit, but
Yeah.
why such a small data set? Why not just use a massive data set like everyone else?
That's a great question, and it gets to the heart of what this research is all about. They were exploring this idea of test time scaling, which means you're strategically applying additional computing power during testing to kind of enhance the model's reasoning ability.
So instead of making the model bigger, you're giving it a temporary boost right when it needs it most.
Yeah.
I like that. I'm starting to see why they call it simple then. But how do they actually do this test time scaling?
So they developed a technique called budget forcing.
Budget forcing.
Yeah.
Oh,
Think
yeah.
of like a coach pushing an athlete to
Yeah.
keep going, even when they want to give up.
Okay, I can see that. But how does
Right.
that apply to a language model?
So let's say the language model is working on a problem, and it's reached its limit. It's ready to give up and just submit its answer. Budget forcing kind of steps in and says, not so fast. You've got more in you. It forces it to keep thinking, explore different avenues, really exhaust all possibilities before it settles on a solution.
So it's like preventing it from quitting prematurely, pushing it to really dig deep. But doesn't that require like a ton of extra computing power?
It does require additional resources during testing, but they believe it's a worthwhile trade-off because that targeted use of compute power during testing can actually be more efficient than just training larger and larger models.
So it's like finding a smarter way to use your resources instead of just throwing more computing power at the problem.
Exactly.
I like it. So to test this approach, they took a 32 billion parameter language model and fine-tuned it on this tiny S1K data set.
Right.
They called it S132B. So what happened? Did all this careful data set creation and budget forcing actually work?
The results were pretty remarkable. They found that S132B was able to outperform much larger language models on a variety of quantitative reasoning benchmarks, including something called the American Immersive Mathematics Examination, or AIME for short.
The AIME. Oh, wow. So you're saying this model, trained on just 1,000 questions, was able to hold its own against like some of the brightest young minds in math.
It did even better than hold its own. It achieved an accuracy of 56.7% on the AA, which is a significant achievement for a language model. In fact, it even outperformed the very system that they used to generate the reasoning traces for the S1K dataset, which is Google's Gemini 2.0 Flash Thinking API.
Wait, hold on. So they're saying that their model actually surpassed the AI system that served as its teacher. That's pretty incredible. But how do we know for sure it was the S1K dataset and the budget forcing? That made the difference.
Well, to answer that, they conducted a series of experiments called ablations.
Ablations.
These are designed to isolate the impact of specific factors.
So they're basically testing to make sure that their approach was really effective and rule out other explanations.
Exactly.
Okay.
So the created variations of the S1K dataset,
Yeah.
each one missing one of their key criteria. So either difficulty, diversity, or quality.
Okay, so like taking one ingredient out of the recipe to see if it really matters.
Right, and what they found was each of those modified datasets performed significantly worse than the original S1K, showing that all three of those factors were really crucial.
It's like they found the perfect blend of ingredients to create this high-performing model. I'm impressed. But is this purely sequential approach with budget forcing, is that the only trick up their sleeve? Or did they explore other ways to enhance performance?
They did explore other avenues, and that's where things get even more interesting. They also investigated the potential of combining this sequential approach with parallel methods, and we can talk about that in more detail in the next part of our deep dive.
Okay, well, I am very interested to hear more about that. But first, we're going to take a quick break, and we'll be right back. Okay, so we're back and ready to dive back into this whole test time scaling thing. You mentioned that the researchers, they were looking at combining their sequential approach with parallel methods. What does that mean?
So with purely sequential scaling, the model is kind of tackling the problem, step by step, building on its previous thoughts. But imagine if you could have multiple copies of the model, all working on the problem simultaneously, each exploring different paths, and then combining their insights. That's the essence of parallel scaling.
So it's like instead of just having one AI expert working, you have a whole team all brainstorming together.
Exactly.
But how do you actually combine the insights from multiple models? Wouldn't that just create a mess?
It could, but they experimented with a few different methods for combining the outputs from these parallel computations. And one approach is actually pretty simple. It's called majority voting.
Majority voting.
Yeah.
So you just run multiple copies of the model, let them each come up with their solution, and then just pick the answer that appears most often.
Yeah, it's a very straightforward approach.
Yeah.
But it can be surprisingly effective. The idea is that
Yeah.
if multiple models, each with slightly different perspectives, arrive at the same answer, it's more likely to be correct.
So it's like the wisdom of the crowd. But for AI,
Exactly.
I like it. But you mentioned that there were other methods as well. What else did they explore?
So they also experimented with a more sophisticated technique called rebase, which stands for rewarding better solutions and abandoning suboptimal execution.
Rebase.
Yeah.
Okay, that sounds pretty intense.
It involves using a process reward model to evaluate not just the final answers, but also the reasoning process behind each solution.
Process reward model. So break that down for me.
Okay, so imagine you have a panel of experts working on a problem. A process reward model wouldn't just look at the final answers that they came up with. It would actually analyze the steps that they took, the logic they used, the overall quality of their reasoning, to determine which solution is most likely to be correct.
So it's like having a meta-expert, judging the work of the other experts, not just about getting the right answer, but about showing your work, so to speak.
Right. And rebase allows you to kind of assign a score to each computation path, essentially giving you a measure of confidence in the model's reasoning.
So by combining the sequential scaling, the budget forcing, and then adding these parallel methods like majority voting and rebase, it's like they created a supercharged AI thinking process.
Well, that's a great way to put it.
This is all very cool. But I want to go back to something we touched on earlier, this S1K data set, this collection of just 1,000 questions. It seems like it's really at the heart of their success. You mentioned they were very careful in how they selected those questions. Can you walk me through that process?
Sure. So they actually started with a much larger pool of questions, over 59,000, sourced from a variety of existing math and science data sets. And then they applied this really rigorous filtering process to narrow it down to the best of the best.
So they had this huge mountain of questions, and they had to carefully sift through it to find the hidden gems.
Right.
What were the criteria for making the cut?
So they focused on 3 key criteria: difficulty, diversity, and quality.
Okay, that makes sense. But how do you actually measure something like the difficulty of a question for a language model?
So for each question, they tested it using 2 different pre-trained language models. And if either model could easily answer the question correctly, they considered it too easy and discarded it.
So it was like a preliminary round. If the student models could solve it without even trying, it wasn't tough enough to make it into S1K.
Exactly. They also looked at the length of the reasoning trace generated by Google's Gemini Flash Thinking API.
Reasoning trace. Remind me what that is again.
Yeah, so it's basically a step-by-step explanation of the thought process behind solving a problem. So the longer the reasoning trace, the more complex the reasoning required, which means a more challenging problem.
Okay, so the longer the reasoning trace, the harder the problem.
Exactly.
Got it. What about diversity? How did they make sure that the S1K dataset covered a wide range of topics?
So they actually used an AI system to classify each question into one of 50 different domains, according to the mathematics subject classification system, which covers a vast array of mathematical and scientific topics.
50 different domains. Wow, they were not messing around. Okay, and then the third criteria, quality.
Right.
What makes a question high quality in this context?
So quality refers to the clarity and detail of the accompanying reasoning trace.
Okay.
So they specifically chose to use reasoning traces
Yeah.
generated by the Gemini API because it consistently produced really high-quality step-by-step solutions.
So it's not just about giving the model a hard question, it's about giving it a really clear example of how to solve it. Okay, so they had this massive pool of questions, filtered it down using these three criteria: difficulty, diversity, and quality. But how did they actually pick the final 1,000 to make S1K?
So for the final 1,000, they used this two-stage sampling process. That balanced all three criteria. First, they automatically selected any questions that were answered correctly by Gemini and came from specific, high-quality sources. This guaranteed a core set of top-notch questions.
Okay, so they had their core set, and then they needed to fill in the rest.
Right. And for the remaining questions, they used a strategy that actually favored more difficult questions. Within each domain, they would randomly select a domain and then choose a question based on a distribution. That prioritized questions with longer reasoning traces.
So they were really trying to push the models to their limits. Sounds
Exactly.
like they went to extraordinary lengths to create this S1K dataset.
They did, because they really believed that even a small data set could have a significant impact on performance.
And did it.
Well, the results seem to validate that belief.
Okay, so let's talk about those results. Did all this effort actually pay off in terms of better performance? So we've talked about test time scaling, we've talked about this amazing S1K dataset. Now let's get to the fun part, the results. Did it actually work? Did all this effort translate to better performance?
Yeah, the results were pretty impressive. They saw significant improvements across a range of challenging benchmarks. For example, on the AIME24 benchmark, which uses questions from the American Invitational Mathematics Examination, their S132B model, achieved an accuracy of 56.7%.
Wow, that's really good, especially considering it's not a huge model.
Right. And what's even more remarkable is S132B actually outperformed Google's Gemini 2.0 Flash Thinking API.
Hold on, they're saying that their model
Yeah.
was better than the system they used to make the data set.
Yeah, basically the student surpassed the teacher.
That's amazing. But how do we know for sure that it was the S1K data set and those scaling techniques that made the difference?
Well, that's where those ablations come in, remember. They tested modified versions of S1K. Each one was missing one of their key criteria.
Right, like difficulty, diversity, or quality.
Exactly, and they found that.
Mm-hmm.
Each of those modified data sets performed much worse, which confirms that all three elements were really important for their success.
So it was like a perfect recipe.
Exactly.
You take one ingredient out.
And it doesn't work as well.
Right. But they didn't just compare against these modified data sets.
No, they also compared S132B to other state-of-the-art models,
Right.
including some that were trained on much larger data sets. And it was still really competitive.
So bigger isn't always better.
Right.
This is all very cool, but it makes you wonder, could this approach, this idea of focusing on test time scaling and using smaller, high-quality data sets, could it be applied to other things, like not just quantitative reasoning?
Yeah, that's a really interesting question. Could you use similar techniques to improve performance in tasks like writing code, composing music, or even designing scientific experiments?
Wow, that's amazing to think about. But are there any, challenges or limitations?
Well, the researchers acknowledge that. This is really just the beginning. There's still a lot to explore. For example, they talk about the need for better ways to evaluate reasoning abilities in these models. The benchmarks they used are helpful. But there's always room for improvement.
Yeah, that makes sense. Like, as AI gets better,
Right.
we need better ways to measure how good it is.
Exactly.
Anything else?
Another thing to think about is this whole debate about AI interpretability and explainability. Even if we can build models that solve complex problems, it's important to understand how they're doing it.
Yeah, we don't just want a black box. We need to be able to trust these models and understand their reasoning.
Exactly.
Well, this has been a really fascinating deep dive. I've learned a lot. It's amazing to see how researchers are pushing the boundaries of AI.
Yeah, it's a really exciting field.
I'm definitely going to be keeping an eye out for more developments in this area. And that's it for today's deep dive. Thanks for listening.